This is Computing Up, conversations about computation writ large, with Michael Littman and Dave Ackley. This episode was recorded June 28th, 2021.
Hi, everybody. Welcome back to Computing Up. Dave, how's it going? How's your summer been so far?
Well, things have been going pretty well. It's hard to really notice the difference between seasons and, all of that stuff. We're still kind of in our pandemic bubble, even though we're all completely vaccinated and theoretically we should be going out and kissing strangers, but we don't seem to be able to do it anymore. How about you?
I don't think I ever did a lot of kissing of strangers. But and do you feel like the retirement is also kind of part of that? There's kind of less crisp delimiting between.
Well, certainly, being a professor, that just continues the whole September is more important than any other anything because it's when school starts. And so, ever since from 5 to 60 or whatever, it was all about September, basically. But yeah, certainly, this is third, fourth year of retirement. It does start to erase the whatever. I'm all about the T Tuesday updates. Every 2 weeks I have to report to my tiny little fans, tiny little army of rebels about how the research is going. So we're still several days away from the next update, so that's good.
All right, well, hang in there. That's the way to do it. I'm actually teaching for the first time in the summer, which is a very unpleasant experience.
Absolutely. That's unpleasant for all involved.
Yeah, poor students, man. And I'm lecturing, over Zoom, so it's like talking to a wall. It's not ideal.
Right.
But to make things awesome, we have a wonderful guest today. And so I'm really excited that we're able to have on George Konidaris. He is a computer science professor in my department at Brown University, but I've actually known him through several of his moves before he came and joined me here. And he's just super fun to talk to, super interesting. And I just really wanted an opportunity to introduce him to you, Dave, and have a fun conversation, all three of us.
Cool.
So, George, welcome onto the show.
All right. Thank you, Michael, and thank you, Dave, for having me. It's a great pleasure to be here, to hang out with the two of you.
So, yeah, no, it's great that you made time. I understand you're in Martha's Vineyard, so that sounds very, posh.
Yes. Yes, the main feature of the island so far seems to be very nice ice cream parlors and also ticks. These seem to be, both seem to be endemic. And maybe there are more of them than strictly necessary, but the very best class of both. So.
Oh, that's terrific! I'm so glad. Ticks are definitely very hot this time of year. So, and I also find that it's there's ice cream parlors and there's places that do seafood, and then there's places that do ice cream and seafood, which doesn't make sense to me from kind of a culinary perspective, but from an opportunistic who you selling to perspective when you're at the beach, it does make a lot of sense.
Not in a single dish, you're talking.
I don't know. I mean, you can order what you want. Lobster roll, lobster Eskimo roll.
Oh, right.
So I did see a lobster ice cream cone somewhere, I think, but I think it was roughly what you would expect, which is ice cream with bits of lobster in it, which is. I guess it's a thing.
That is not what I was expecting. I was literally not expecting. Because there's a flavor called lobster tracks, which is just normal ice cream, but it's got a lobster, name.
It's got red ribbons in it instead of chocolate ribbons?
There's bear tracks, which are peanut butter cups in vanilla ice cream. And then there's lobster tracks, which is I don't even know, something else. Maybe there's raspberry, so maybe it does have a red thing going.
Right.
Honestly, that sounds like a much better idea. They should have stuck to that.
So George, you work in robotics and also artificial intelligence, and robotics and artificial intelligence at the same time. And you also think pretty deeply and in interesting ways about the AI problem. And that's kind of what drew you to those two topics in the first place. So can you tell us a little bit about the kind of work that you've done and what you're doing and what you hope to accomplish?
Sure. So I wanted, there's the big AI problem, right? There's solving the complete intelligence problem, which is that I would like to build an intelligence. And because I was born far from America, I'm South African, in case it's not obvious from my accent. And when you're born in one of these sort of far-flung places, you just sort of figure, well, it's improbable that I would be likely to be a computer scientist or do anything like that. So I might as well just go all the way and all the way to the improbable. So,
Sure.
I've always tried to think about how you could build a generally intelligent robot in the way that that you are. So I should say, first of all, that means a robot, not a computer, because there aren't, computers are in AI. Computers are sort of analogous to brains, right? But there are no brains running around in the environment. There's no brains hanging off trees or brains running around in the fields or floating through the air. There are only animals, and animals are robots in this analogy. And so for most of my career, I've been trying and failing to build smart robots and robots that learn. So mostly I've been building robots that fail to learn and are pretty dumb. That's a fair summary, I think. Well, they're not.
Wouldn't a computer just be a really, really lazy robot?
I guess so. Yes, I guess you could. I guess so. But it's got to have inputs and outputs, right? Otherwise, it's a rock or something like that. And the inputs and outputs have to be attached to the world.
Yeah, or at least hopefully you think one day it might be able to talk.
I guess so. That's an actuator.
Yeah, exactly. And this is an argument I used to have with a friend of mine that I would say that you had to be embodied. You had to have a stake in the universe in order to really matter. And so he would try to take it down to the absolute limit of the least possible stake in the universe. Like all he's got is one LED that he can turn on or turn off, and that's it. And could that be a robot? Could that be artificially intelligent and so forth? Well, yeah, but I don't want to spend my career on it.
So this is one of the things that the field does, right? So if you open Russell Norvig, it says an agent is a thing that has actuators and sensors, and then it says, and there's an agent program. And so then, and then one way to summarize, if you were to be cynical, the field of AI is it's a bunch of people running around fitting that to the problem they think is interesting. So if they want to do image recognition, well, the sensors are a single image, and the actuators are one of three classes.
Yeah, right. And say yes, say no, say maybe.
Yes, exactly. And I guess that formally fits the definition, but everyone knows that that's not what we mean. And one of the things about being an AI is that we have to accept that we don't yet have good formalisms for exactly what we mean yet. We're sort of a little pre-scientific in that we don't have the problem nice and well defined. But in many cases, if we are genuine about it, we know what we mean. And so I remember actually in grad school we used to have like multiple hour arguments about whether or not a rock rolling down a hill is a robot or a thermostat is the classic example, and all those were interesting and fun to think about the edges of definitions in the math way that computer scientists like to, but it's never actually what we mean, right?
Yeah, it's not what you want to actually do for engineering. That's something that you do over a beer and then you get to work, and you've got to make such a raft of other assumptions to actually start doing any work that's actually the more important case.
Wait, so then if that's too small, if that's below the limit, what's for you the limit is it should be able to like move things around in the world, like do productive work, or does it have to be like everything like a human, like everything a human can do, it can do? What's your bar?
So that's an interesting question. So I don't think I have a good, I don't think I have an explicit description of the bar, but I do have a fuzzy classifier that says this is more likely to be what I mean, and this is less likely to be. So maybe we have a sort of spectrum of interest, right? And so meaningfully being able to modify the world, I think is a reasonable guideline to that kind of line.
So the LED robot could do it if the LED itself was attached to something that could do something in the world, right? Like if it could then, there was a photoreceptor that would actually drive a motor.
Connected to the Planet Buster bomb. All it's got to do is blink its LED and boom, we're all dead.
Yeah, or it's binary signaling, and the signaling gets interpreted by a robot, and the robot can do, you just need a one.
But then at the end of the day, that effector really matters as part of the system for you.
Yep. So I think if we take the embodied thing seriously, we don't try and wave away the embodiment and say, well, there's some embodiment. What do we, how complex is the program? We need to say, as a whole property of the sort of physical plant and the processor together, how intelligent or how broadly capable these things are. So now I'm going to go on a flight of a couple of vague math analogies. Please forgive me, all my undergrad math instructors, for how vague these are. And this is sort of inspired by this, when I did my master's, and I did this at the University of Edinburgh, which is, I think I met Michael shortly after I graduated from there, but we got to hang out in Edinburgh some, which was a lot of fun. there was this whole embodied AI animat thing going on, which I still really enjoy. And one of the arguments that they would pose is they would say, well, what about it? You need to think about the ecological niche of the agent. So you've got a dung beetle, and dung beetles are amazing at being dung beetles, right? Given that that's your embodiment, and given that your objective function is, I don't know, accrete dung, dung beetles are like, they maximize that objective function given that hardware. You really couldn't do any better at being a dung beetle. But then when you get more complex morphologies, the sort of range of problems that you can solve is larger. So one way to think about how intelligent an agent is out of the space of all things you could ask it to do, what fraction is it physically capable of? And then of the ones that it's physically capable of, sort of how does it do on some objective function in those? And you could imagine like some kind of area measurement, right? And so most embodied agents can only do one thing, and so you can maximize intelligence by just being maximally good at that one thing, like a dung beetle. But then as you get more general actuators and sensors, you get a wider range of things that you're able to do. And then you can sort of say, okay, conditioned on that being the physical set of things that you can do, how smart is the agent? And that has something to do with how many of those tasks it can accomplish in time.
So it makes me... So is it the actuators and the sensors to focus on, or is it necessarily that plus the entire environment that the thing is going to be in? Because I keep thinking about, I'm a super genius, but not in the middle of the sun. Mm-hmm. I really can't do anything intelligent in the middle of the sun. And if I was to pick locations in the universe, most of them are dead space. So I'm really not going to do intelligent very well, at least not in my current outfit. So is it really... hard to know what I want to say. Do you think it might be possible to actually come up with a definition of intelligence that has something to do with the fraction of environments in possibly considerable where this creature could make a go of it, and that if you have a more, that kind of thing?
Yeah, no, I think that's right. So the definition of ecological niche includes the environment that you're in. And often it includes like the distribution of a task. Now that's not really well defined for an animal, right? Like an animal just wants to reproduce or whatever. But you could imagine saying, okay, across what fraction of environments and what fraction of tasks across that environment is this set of... And then you would say, for this given set of sensors and actuators, is this agent program able to do the right thing? And dung beetles are great in their very small ecological niche, but you increase the temperature by 5 degrees and they will die. And so so that puts them in a sort of relatively narrow thing.
Right.
But one of the things that I think is exciting about and to swerve off a little bit here, Michael and I sometimes talk about the sensory motor dilemmas. What makes general intelligence interesting is the idea that you have an agent whose sensors are not perfectly adapted to a single specific task, but rather are kind of way unnecessarily general for any specific task because they have to solve a wide range of tasks, right? So you can imagine that if you're a thermostat, you just need the one sensor and the one output, and you can perfectly adapt your sensors and your actuators to your task. But if you're a human, you don't have a chest sensor. You don't have a thing that immediately tells you what the right state of chess is. That says, okay, I'm looking at a chessboard. It's an 8x8 array. Here are the 6 types of pieces and their colors. And you don't have a chess actuator which moves the pieces legally. Instead, you have fingers and hands and arms and high-resolution image sensors, which are crazy, right? There's almost no individual problems for which you need that complex a sensory motor apparatus. And so the fact that we have one tells you that we are, in some sense, evolved to be able to handle a very wide range of tasks.
Right.
But then you have this trade-off, right? So you have and I think that this is sort of one of the key questions of general AI, which is something that I like to think about because that's what I got in the field to think about. One of the key sort of things to deal with there is if you want to be able to solve any problem with a single agent, then you have to deal with this dilemma. You have to say that agent sensors and actuators are going to be totally wrong for any individual task. And how do you kind of learn a representation that lets you focus in on what's important for that task in that kind of narrow setting? I don't know if that makes sense, Dave. Michael and I have talked about this a lot.
Well, for sure, I'm all with embodiment. I'm all with what you can do. I wasn't exactly sure what the dilemma was, the sensory motor dilemma part of it. That, sure, every sensor is going to have trade-offs in generality and cost to construct and maintain the sensor. Same thing with the motor. But no matter what, it just gives you access to a tiny subset of the entire possible environments you can imagine in the universe. And so the idea is, if you were going to be optimized for being a dung beetle or whatever the heck it was, then you wouldn't spend evolutionary resources or developmental resources on a high precision eye. You would just spend it on a dung beetle nose, to a dung smelling nose, or whatever it is, and you'd be good at that.
But that's not the dilemma, right? The dilemma is not about the evolutionary cost.
Thank you.
Although that is important and useful, there is an energy cost and all that stuff. The dilemma is about the more general purpose and agent you are, the less suited your sensors are to any individual problem that you face.
Is there a downside to being so you're saying my incredible eye will not do as good a job recognizing dung as the dung beetle dung nose sensor will do, because it'll really do it. So I'll do a strictly worse job, but I'll be able to smell lobster ice cream as well.
Or it's a harder job computationally, right? It might not be that you do strictly worse. It might be that you do exactly the same, but you have to devote compute resources.
So more resources to do what this other thing does much more efficiently.
Yep.
Like that. Okay, so that's the dilemma. It's generality versus efficiency, or something like that.
Yep. And so I think that this is the mistake that we make in AI all the time. Is that we are, when we're trying to apply AI to a problem, we assume that the problem's already framed for the agent, right? We assume that you go in with a chest detector, or you go in with if you're learning to play soccer, you go in with a thing that measures the distance between soccer balls and players and closest 5 players and all that stuff. But that's not the case at all, right? If you have a general purpose agent, you're stuck in a dilemma. Your sensors do not do that for you because you're a general purpose agent. And so the agent has to construct that itself. It has to frame the problem itself to get it into this kind of nice, this kind of well-framed problem setting.
When I was poking around the internet at your stuff, just trying to see what you were about, the thing that I landed on was this whole, sort of abstracting symbols from a point cloud or from some lower level data representation like that, which certainly appealed to me because it seemed exactly like that, when I was a kid, it was classical AI, which is we're going to shaky the robot and Block's World, and we're going to model the intelligence as a model of a mind, and the mind gets symbols to start with, and that is setting up the problem in exactly the way that you're saying, that the experimenter, God, somebody, predetermines the nasty, noisy, buzzing physical universe and boxes it into these clean little symbols like an X and an O and 9 squares, and that is not the whole story, and maybe it's even in some sense the less important part of the story, depending on the angle that you come at it from. So are you going to tell me that you have a way to do the other half of that problem, to start from the blooming, buzzing confusion of the physical universe and tell us what the symbols are?
Yes, with some caveats. So
one little asterisk.
One asterisk. Yeah. But first I want to say that that's exactly right. I think that it's something like, in my guess, something like 80% of the problem is getting to that representation. And the reason that I say that is because in AI, we really study the wrong thing. We study like being superhuman at stuff, and so that takes a lot of effort. It's very hard to be superhuman at chess, but that's not actually interesting, in my opinion. It is interesting, but it's not the problem. The problem is to be about as good as the average chess player or average person at everything. Right. And actually, a fairly generic alpha-beta pruning algorithm does as well as your average club chess player once you have that representation. So in many, many cases, including some very hard things, we can do about as well as the average person out of the box once you have that representation. It only gets hard when we say we want to beat Garry Kasparov or something like that. That's when we need to put in like 20 years of effort and make the world's best algorithms. But most the vast majority of people on this planet can't ever aspire to that, and that we consider them intelligent anyway. So I think that the emphasis on sophisticated algorithms that get us to superhuman performance is wrong-headed. And actually, we should be able to say, well, we've got pretty good algorithms. They get us to sort of almost average human performance in many cases, but they assume this representation.
Right.
They assume that someone drops in and says, "This is chess. It's perfectly defined for you. Go." That's that pun unintended there. Checkers. Or checkers, yeah. but I think that that's the thing, right? Is that having that representation is the key thing. And so if you write this all down as a reinforcement learning problem, and that's the sort of formalism that I work in, then it actually becomes a well-defined problem. You could say you've got a Markov decision process, there's states and actions and a reward function. And then you can say, okay, I've got an agent, and that agent's got a very high-dimensional perceptual space that's a very big state space, and a very high-dimensional action space that's a very big action space. And those are the same throughout its lifetime. It never changes because it's always one agent. And we're going to change the task that it's facing by giving it a different reward function each time.
And so, just to push in for 1 sec, so when you say a set of actions, to me that sounds halfway to symbolization already. But what you mean by action is one more joule of energy sent to one more stepper motor or something like that, not pick up the red block.
Yeah. I mean, actuate your joints. So usually it's a real valued vector. I shouldn't have said set.
Okay, all right. So it's not even really a set of actions. It's a space.
Yep.
Okay, all right.
Space of sensations or observations in space of actions. And I think you can make a pretty good argument, and we won't get into the art details here, but with a few embellishments, partial observability being one, that's like what a robot actually does. When a robot gets shipped to you, you've got some hertz, that it updates its sensors for, and you get a real valued vector. And there's some hertz that does control that, and you get a real value, and you output a real valued control vector to those things. And that's the actual model. That's actually what's going on.
Right.
But of course you don't ever want to do decision making at that level, right? That's crazy. It's really
well,
terrible.
it has to cash out. There has to be a representation all the way down till eventually what you're doing is real time system control.
Yes.
At some interval, some periodicity, whatever. Go ahead.
Yes, I would say you're doomed to interact with the world that way. You have no choice, right? But you'd really rather not make your decisions at that level.
You don't have to interact with the world at all. You can just die.
Right. But once you write down this formalism, you can say, okay, now I want to learn a problem-specific description of the world, and it should look the same. It should be a set of states, a set of actions, and a reward function. But the reward function should be the same because it's the same task. Mm-hmm. And the transition function, which describes how the world works. But the transition function just describes how the states and the actions change the world. So the reward function and the transition function sort of happen once you've got the states and the actions. So it's really a question of mapping your high-dimensional state space down to a low-dimensional state space that we call state abstraction, and mapping your high-dimensional action space to a low-dimensional action space that's action abstraction. And what my work
none of those mappings are really forced on the robot by the universe in any direct sense. It's a choice that the robot has to make and take the consequences no matter what.
Yeah, exactly. It's building a model, right? And models are only ever useful, right? They're never accurate. And so,
as Michael likes to say,
yes. We do have this advantage if you have a reward function that we can say formal things like this is a reward function. This is a choice of abstract actions and abstract states that gets you a higher return as measured by that reward function. So what my work does is it shows that if you have the action abstractions, then I can get you the state abstractions. I can get you the symbols. That's a sort of well-defined math question, because you need to say, okay, what do I want to do with those actions? Well, I want to build plans out of them. I want to be able to evaluate the probability that plan is going to work and the expected reward if it does work. We can formalize what classical planning would or probabilistic classical planning would ask from the planning process, and then we can build symbols that sort of provably support that computation. So if you give me the one, I can build the other.
And how does that not founder on combinatorics and exponential numbers of exponential numbers of exponential numbers in every possible step of that process? Okay,
so building the actions, let's leave that aside from now, because that's very hard, and a lot of people, including me, wrote PhD theses on that, and we're getting that. For building the symbolic representations, you can show that there are some circumstances under which you don't get a combinatorial explosion, because now it's a well-defined math problem. So now we can say, okay, I can formally prove some stuff about this, and one of the things I can prove is when is the number of symbols roughly linear in the number of actions, and when is there a combinatorial explosion. And there are cases where there is a combinatorial explosion, and there are cases where you get uncountably infinitely many symbols, right? So you can't always get to a discrete state space. You can't always get to a compact discrete state space because it's unreasonable to expect that you can do that. Some problems you have to have a real valued action space. Some problems you have to have a real valued state space. Some problems you really have to do at the lowest level. There's just no way around it, right?
Okay.
But we can say, okay, under some circumstances, if your actions are built a specific way, if they have this kind of funneling structure where you can execute them from a lot of places and they land you up in a small number of places, and the small number of places they land you up in don't change most of the state variables in the world, but only change some, then you get a nice factored representation, and you can do classical planning with it.
Okay, so I'm still, it makes sense to you, but I haven't quite got it yet. So you were saying, there can be pathological environments where, everything remains infinite order or extremely high, and there's nothing you can do about it.
Yep.
But if there is redundancy in the universe, if there is lots of different ways to the same result, and once you isolate the result, then you can get some leverage. Where actually did a symbol come into that? Where was it that suddenly there was a symbol that there wasn't before?
Right. So in my head, state abstractions and symbolic representations are the same thing.
State abstractions and symbolic representations are the same thing.
Under some circumstances, right?
Just try to get it. And so the question is how you go from a high dimensional, real number, real valued state space to
small discrete
blue block, whatever it is.
Yep. And so the way to think about this is it's a sort of perceptual abstraction, right? And it says, okay, you're observing the world, but you're collapsing a very large number of these potential observations into one discrete thing, right? So one way to think about
more or less discrete.
The blue block is on the red block. There's a very large infinite set of observations you could see. For some subset of those things, your little blue block is on the red block detector goes off. You've got a little classifier that says ping, blue block is on the red block. So now there's two ways to view that. One way to view that is you've got a classifier that tells you symbol is true, ping. And another way to view that is you've got the set of states in which symbol goes ping. And so one is like the intentional description and one's the extensional description, but they both describe a set. And that's the classical semantics of a propositional symbol, is that it's a set of states in which the symbol is true. Right. So we're taking
somebody had to make that filter. Somebody had to decide that filter was a worthy filter to have.
Right. Well, so what happens in my work is we build the set of filters that are necessary and sufficient for planning with your abstract actions.
So go ahead.
The magic transition, because Dave's asking sort of like whence the symbols, like where did they magically appear? And I think in the work that George is talking about now, a person decides on a set of these abstract actions, right? These things that, like, I don't know, they have a bunch of different names, options and skills, but basically there's like if I'm doing this thing, this is what happens. That decision about how to break up the world into those behaviors then induces a way of breaking up the world into states.
But was that person a researcher or a robot?
So actually, this framework is agnostic to who provided the skills, right? So
as long as somebody does.
As long as somebody did. At the moment, it's a person. In my
researcher.
Journal paper that a lot of this is in, I went and handwrote the skills.
Okay.
But we do have a whole line on how you discover skills, a whole line of research on how you discover skills by just interacting with the environment. And the nice thing about that is it's also a sort of well-defined problem, right? You want to say, what set of skills would allow me to solve this problem very quickly with minimal value loss, and maybe I've encountered different instantiations of this problem over time. I've played 5 or 10 chess games by twitching my joints, and now I want to say, okay, what are the skill building blocks that I should have constructed in retrospect that would have allowed me to do very effective decision making on those previous chess games, to make sort of high level discrete decisions rather than low level joint decisions. So it's a well defined problem. It's just very hard.
Right.
And so I think we're at 30 or 40 PhD theses written on skill acquisition, including mine, and we're making progress. We can discover them in kind of robot-like environments in simulation but it takes like thousands of episodes. So not practical just yet, but at least in principle, it's not impossible to do. And then I think humans cheat a little bit in the sense that we learn them mostly from each other, right? Very few of them, except maybe the first layer, we learn completely from scratch. Like babies are waving their hands around and they're figuring stuff out from scratch. But, if I teach you to play chess, in the linguistic description and the demonstration I give you when I do that, you can glean a lot of stuff out.
Right. Yeah, I mean, certainly there's all of this existing conditioning that no matter where you cut the problem someplace, there's a teacher upstream, there's evolution upstream, there's earlier physical interactions upstream, whatever it is. It's just a question of how completely, what's the explanatory burden of the stuff that you're cutting away versus the stuff that you're actually moving the ball on. I mean, so that robot that you had that was going between the ice chest and the cabinet back and forth with the green cup all the time, is that a skill acquiring thing that we were looking at there, or is that a higher level thing?
I built those skills. I built those skills by hand with a motion planner and a little bit of computer vision.
Right. For the people who haven't watched the video, unlike, say, the three of us. So this, where were you when you did this work? Was that at UMass?
I was at Duke.
No, it was at MIT. I was at Duke.
No, it was at Duke.
There we go. Duke. Yeah. Okay. All right. So you had a robot that could roll around, and it had gangly arms, and you programmed it to be able to open and close a cabinet, open and close a cooler, and to lift a water bottle or something out of the cooler, and it could put things in the cabinet, it could put things in the cooler. So it had this set of skills, right, that you constructed.
And there's a switch it could open and close.
Right. Okay, that turned on and off a light.
Yes.
The light
in the cabinet.
There was a light in the cabinet, which prevented the robot from being able to see anything in the cabinet. So,
all right, but the interesting thing about this is that even with all those skills, there's still a hugely high dimensional state space, a lot that you have to reason about to chain things together to accomplish anything. Like, for example, taking the bottle out of the cooler and putting it in the cabinet.
And push the button and open the door and just getting all of that.
Because of that, right? Because of the environment being what it is, you have to chain these things together to accomplish just what would otherwise be simple. Just put it in the cabinet. And now, to do that, you have to do this. To do that, you have to do... I think Dave calls it yak shaving sometimes, or maybe it's not related to... I don't
that's not
completely
my phrase.
understand
that's the universe says that.
The universe calls it yak shaving.
Yes, absolutely.
Certainly,
the non-yak
PhD
universe
student Jessica calls
it
yak shaving. I don't understand how to use that phrase successfully, but it evokes in me the sort of idea that I can't get this done unless I do this other thing first. And the robot faces that. And so if it's just trying out things at random, it's really never going to get it done. It has to reason its way through this long chain to actually know what the first right step is to take. And so it constructs a state space, it plans in that state space, and it actually is able to accomplish the task.
And the state space is very small. Is the key thing. It's written in a language that looks like strips. So it's ultimately that's right. After it's done the learning, it has this abstract state representation, which is a text file. So it's inarguably symbolic. But that's kind of provably sounded complete for planning in the low level thing. But its original perceptual space is just voxels and joint positions in a position in a map.
So pretty close to physics at that point.
Yeah, sometimes I call this going from soup to knots, right? Because it's like all soupy and indistinct in the beginning, but at the end you have logical operations like knot you can do.
Oh, I thought you meant like the universe gets tied together into knots, like overhand knots and square knots that where it brings a whole bunch of stuff together. Rather than negation.
That's clever.
I mean, because it's like a symbol. Knot sort of brings a whole bunch of stuff together.
Like those little hair things that some people have.
Like
it's
knots.
like it brings all your hair together in a...
Exactly.
What do they call that?
All the threads. You call it a knot. I suppose people call it a tangle, but soup to tangle doesn't sound so good.
It doesn't have the same rhythm. Sorry.
All right, so the robot video with the thing and the cooler and the thing, that's an example of a higher level stuff, not necessarily the higher level stuff, because could be meditating on the meaning of beauty would be a higher level still, but the skill acquisition stuff or the skill representation that you were just talking about was a lower level stuff, more part stuff that you were sort of directly writing as the human, as the researcher in that video. But since then, there are poor little PhDs, beating their heads against all these aspects of the lower level task with enough success that they go on to get their PhDs.
Yes. And so one way I like to think about it is, when you're abstracting state, it's like you're abstracting input, and when you're abstracting actions, it's like you're abstracting output. And so it makes sense that if your output is made much smaller, then you have the opportunity to shrink your relevant input, right, to the decision process. And so that's kind of how we've been thinking about that. But I wanted to latch onto something Dave said earlier, where you said like that's a higher level, not the higher level. Because you mentioned GoFi and the sort of the old days, and it's useful, I think, to think about why that failed. And one of the reasons why I think that failed, which ties nicely into the sensory motor dilemma, is that it's a mistake to think that there's one such description of the world. It's a mistake to think that there's like one abstract description, and that's just going to be able to capture everything. And if we just got the right one, then we could roll, basically. Right. And then, whenever everyone tried to do that, they quickly ran against the limits of a single representation, right? They're like, oh, it doesn't quite handle this, or it doesn't handle that, or there's an edge case where it breaks down, or maybe I just didn't choose the right symbolic representation. Maybe I needed a more complex one, but we keep adding in things, and now it's gotten too complex to support decision making. And I think that the real answer is that you just need the representation that's right for that specific problem, and they don't have to be the same across all the problems, right? It should be the case that you learn the abstraction that's right for that task. If you want to play chess, it looks like this, and if you want to kick a soccer ball, it looks like that, and if you want to find your way through a city, it looks like this, and if you want to if you want to learn to juggle, it looks like that. And some of them are discrete and first order and have this logical flavor, and some of them are real valued and look like a control problem. And it's unreasonable to expect that there'll ever be a single true one, because if there was, then the agent would have that thing as its inputs, right? It would have been designed so that was its input and output space because it captured everything. But the reality of the world is that that's not the case, and all our models are approximate, and so we should, but maybe useful, and so we should find the useful model for that particular thing and that particular problem and run with it in the context of just that problem.
So you're saying that there's no perfect solution for many reasons, including sensors are always limited. You can't sense everything, and if you could, what would you do with it? And similarly, your actions are limited. So at the very least, or at the very best, any representation for problem solving or symbolic representation or whatever is all completely contingent on the limits of your sensors and has no impact other than the limits of your effectors, your motor skills like that. So we should just get over the idea of abstract reality outside in the universe, objective reality, or there is a Platonic behood out there. There isn't. It's whether I get bit by it or whether I can get its honey, and that's it.
No, that's not quite what I meant. So, although it has a similar flavor, I do think there is a Platonic objective reality, but I think it's low level, and I don't think that you should expect to be able to abstract over it.
I see. So it's quarks and photons and wave equation evolving in space and time.
Yep. And everything else, every higher level thing you put on top of it,
that's on us.
Just a model, and it's not true, but it may be useful. And in particular, I think most models are useful in a very limited context. Like they're predictive and they're a good model of what's going on in a very narrow context. And so whenever you build a model, it should be built for a context and for a specific problem. Like it is the case that you can build a nice logical representation of chess, and it's discrete, and everything's lovely, and it's not stochastic. But then when you build a model of backgammon, it's stochastic. And now you've just got to have to deal with a different representation and a different set of solvers. And if you want to learn to play soccer on a real robot, it's real valued, and it's not logical anymore. And so I think we should let go of the fact that there is an abstract symbolic reality. I don't think that you can write down like a first order model that captures everything about the world. I think all abstractions are going to fail on top of eventually. And so what we should be doing is we should be saying, okay, for this particular reward function, which describes a task, this is a good model. And it might entail representational commitments, and maybe the representational commitments aren't suitable for some other model. And it might entail restrictions on the actions that you can take that are reasonable and restrictions on the states that you can differentiate. But belongs to that reward function in that task, and it doesn't get necessarily applied to another one. Does that make sense?
So, sure, I think.
So it's not a statement about reality. It's more a statement about the suitability of models.
Right. Well,
I feel like you're saying think local, but perceive and act global. Right. So you perceive and act in the actual world, but when you're actually contemplating what to do, you do that in your model of what's going on, which can be greatly simplified and only needs to be relevant to whatever your current task is.
Yep.
It doesn't have to be all encompassing.
Yep, that's exactly right.
Where it was making me go was, well, okay, it's all a model, sure. And a chess model is different than a soccer model, is different than a cooking dinner model. But that doesn't mean there aren't relationships among models and that there aren't generalization relationships. It's not to say every model is sacred, every model is equally good, so I'm just trying to push back toward the hierarchy people again, saying, well, there could be the one dominant model, the one that's the best, least worst, and that would be unique. And if we could just think about that, then we would be super intelligent and we would turn all us people into paperclips. So is that not true? Is that there isn't the best model in terms of, yes, they're all approximate, but there's a single best one out there to be found?
Yeah, I don't think there's a single best one out there to be found. And here's my reasoning. So the one true model that describes the sort of interaction of the robot with the world is something like a partially observable Markov decision process with a reward which describes the robot's interaction with the world, its sensors and its actuators. And then the reward function changes per task. And we all know that POMDPs are just incredibly hard to solve, right? So it's a maximally descriptive model, but but by the same token, it's maximally hard to use. Right? So the trade-off is such that it captures everything that you want to do with the world, but it's also extremely hard in the general case to do anything with that.
Because
it takes too much data to infer, or it's a combinatoric problem now?
Well, Michael can tell you about the computation results, but they're ominous. Let's put it that way.
Okay.
I think it's all those things, right? I think it's the more if it's more complicated than it needs to be, you're going to need more data than you need. You're going to need more computation than you need. It's just all the costs go up.
And so I do happen to think that's the sort of Uber model, right? That is that actually describes what's happening in a robot. It actually describes what's happening with you and I. But I think if you look at special cases of that model, what you find is so let's say you learn an abstract representation of a POMDP. You get a new POMDP, but it's very compact. If that POMDP happens...
POMDP, for people who don't know what a POMDP is, partially observable Markov decision process, just basically a problem space that a mathematical problem space where you don't know exactly what you're seeing. You have to interpret things perceptually, which is a more general model, but it's really hard to solve.
Yeah, it accurately models what's happening in a robot. You have sensors, but they're not perfect. They're noisy, and they've only got local kind of receptive fields, so you don't get to see everything about the world. Now, if you say that in the problem you're facing, everything you can see is everything you need to care about, then it collapses to an MDP, which is a Markov decision process for which we have good algorithms. And then if you say, okay, a Markov decision process includes stochastic transitions, and it's potentially real-valued state in action. Now, if it happens to be discrete state in action and deterministic transitions, what you have is a search problem. Now that's something that you can apply A star to. So now it's a very restricted subclass, but we have really good algorithms for that. And if it turns out that the action space and the state space are factored, and it's deterministic, then you've got classical planning, and we have really good algorithms for that. And if it turns out that it's not a sequential decision process, that you only ever get to take one high-level action, then what we have is a bandit, and we have really good algorithms for that.
Nice.
And if in addition to the bandit you have demonstration data, what we have is supervised learning, and we have really good algorithms for that. And so I think what you find is there's this trade-off between how general the model is and how good the algorithms are that you can apply to it. And so what you want is an agent that builds that model for itself, and then because it's built it for itself, gets to look inside and say, hey, I see that this mapping is deterministic, or I see that under these circumstances this is actually Markov. Now I can swap in a really efficient computational algorithm Like if it's classical planning and we can build a heuristic, we can do, zillions of states. That's not very hard. But if it's an MDP, we maybe can't do zillions of states. And if it's a PondDP, we can do like 20. And so what you find is that the Uber model is just intrinsically incredibly hard to use. It's just not computationally. There's a trade-off between representational power and computation, which is what you would expect. And then as you get these special cases, you start to lean more towards computation becoming efficient, but the representation not being general. And so that's why you have to learn these kind of problem-specific things.
And chances are the assumption of you have complete observability versus being partially observable, or all the other ones that you mentioned, that was really great, are not 100%. It's like you got mostly observable, so you go ahead and make a Markov process assumption, but there's this residual surprise for you because it wasn't actually entire, and so forth. So you pick your efficiency improving representation and you take your chances because in fact it's not going to be 100%. I mean, if it is 100%, then great, wonderful. You're a thermostat. Go sell thermostats. But for the next step, you're going to have this remaining stuff, and so that's the argument that there's no single peak intelligence. It's not even possible. It's not even well defined, because no matter what you do to be smart, you're going to pay somewhere else. It's a no free lunch kind of thing. Yep. And which of course go ahead.
And that's not unexpected, right? So people often complain that they say, "Oh, POMDPs are very computationally very hard," but it's unreasonable to expect that like intelligence, which can do all this cool stuff, is going to be, like in P or something like that, right? It should be the case.
If it was easy, it would have already happened.
That's right.
And we're creatures who can prove Gödel's incompleteness theorem, right? So we have some level of reach into things that are incomputable. And so, of course, the general model is going to contain like things, some questions in a POMDP are simply incomputable, and we should expect that if we think it's a true model of our input-output. It should be Turing complete, right? Otherwise, it's not the whole thing. It can't be the whole thing.
All right, I wanted to hit
that's
on
a whole other
two last
fish. Turing complete. That's computability. That's computability is evil. Anyway, sorry, Michael.
Yeah, no problem. So I just wanted to hit on two last things before we wrap up. One is I looked up what lobster tracks are. And so it's vanilla ice cream, lobster-colored chocolate cups filled with caramel swirled in unique eclair crunch. There's really very little lobster about it. It's just ice cream, but it's made in Maine. Like lobster colors. So maybe. Yeah, maybe there's little bits of lobster-shaped things in them. And the other one is, I just, while we have George here, like a lot of us, U.S. people, I think Dave and I both fit into that category. Dave's been on two sides of the country. I've been really only on one side of the country, but you've actually been schooled, George, in 3 different continents. And I was wondering if you could just quickly comment on like highlights, like what's a good thing in each of the continents that you've been schooled in. So you did undergrad in Africa, you did your master's degree in Europe, and you did your PhD in North America. What's good about each of those?
Okay, so there's lots of different aspects.
Because and for what it's worth, the reason I'm asking it this way is because for those who don't know, George has a wonderfully bitter, sarcastic sense of humor that he will let out amongst friends sometimes, and he can make everything sound bad. And so we don't need to hear that right now. Tell me something good.
I promise my wife, whenever anything's being recorded, I'll only be positive. So, I mean, I love growing up in South Africa. Of course, I was from a very privileged part of that country, and so it was not the same for everyone. But for me, it was a really beautiful country. Weather was amazing, and I just happened to, by just sheer dumb luck, have grown up in the city with the. In South Africa, it's a bit like Europe. You just go to university in your city. You don't travel far away or anything like that. And I had the sheer dumb luck of being born in the city with the university in it with the best computer science department in Africa. I just kind of showed up, and they were amazing. I look back at the level of undergrad education that I got, and it was almost unreasonably good. I mean, I don't know how they pulled that off. Actually, I know how they pulled it off. They pulled it off through great personal cost and an incredible amount of stress. But I really had an outstanding first-class undergrad education. And there were a couple things that sort of, in retrospect, stick out to me now. part of it was that um, part of it was that it was you felt like this person on the periphery of things in some sense, right? So it's like it felt a bit like Luke Skywalker growing up on Tatooine or whatever, and then someone comes along and says, "Hey, do you want to join this cool thing?" Like being able to go overseas and do a PhD felt like this sort of calling from where things were actually happening that I would get to go visit. But because I was growing up in South Africa, I wasn't programmed with some of the things that I feel like American grad students are programmed. They often feel like this is just a natural part of life that you can go to grad school and you do reasonable things and do fun problems and it'll be interesting. And I felt it as like, okay, this is my shot at like, the biggest, most interesting scientific problem that exists. And, if I can grow up here and end up studying that, like we should just go for the big thing. I felt like, okay, I'm going to go and do my best to solve the AI problem because we're in improbable land anyway. We might as well go all the way.
Go for it.
Yeah.
Whereas I feel echoes of Hamilton somehow. I'm not sure, but that's the feeling. We could definitely make a musical about your journey.
It would. Well, okay. White South Africans are like the
I'm
global
not throwing
minimum.
away my bot. I'm not throwing away my bot.
But White South Africans are like a global minimum for rhythm. So I don't know that would be a good idea. Maybe we'll make like a spoken word musical or something like that. And then when I went to Edinburgh, that was an amazing thing for me because I mean it's just one of the most beautiful cities on the planet, and I loved every second of being there. But
that's great.
It was also this thing that at the time in Europe they had this kind of animat. It was the tail end of that stuff, the animat embodied AI thing where everyone.
I feel
was
like Dave remembers that because we were thinking around in that space back in the day.
Yeah, actually, so actually, if I can take a mild detour. I loved Ackley and Littman 1991. When I was an undergrad, I read that paper and I was like, this is the coolest thing I've ever seen. And I was running around telling people about it. Like I went to the biology department and found my biology friends. I'm like, look at this. These guys have done this thing. And it's amazing how these things that you read when you're an undergrad stick in your memory. I got to give a talk, I think in 2016 at a Nature to Nurture workshop in robotics. And I gave the whole talk about your paper. I was like, look. And Ackley and Littman showed that learning smooths out the evolutionary landscape, but if the agent keeps getting the same task over and over again, it will build in the things it doesn't have to learn them. Look at this line here on this,
All
like
right.
I actually, and it sticks in your head. This is like 25 years ago almost. But it was such.
I would love to see the slides from that talk.
I will send it to you. It was. I actually went right after Leslie, and then I suddenly got nervous. I'm like, Leslie, you're not going to talk about Ackley and Littman, are you? And she said, I'm not sure what you mean. So, because you wrote that before you were her PhD student. So,
yeah, that's Leslie Kelbling. Yeah.
So I guess that's 30 years ago now.
Well, it was 30 years for you, but 25 years for me.
I see. Okay, yeah.
But absolutely wonderful paper. So, but there was that kind of thing was in the air, especially at Edinburgh. We were thinking about that, and I felt like people were thinking about the right questions. I don't know that always the sort of at that time the animat people had the math and the formalism to carry it forward all the way, and therefore I felt they occasionally got stuck doing these sort of architecture diagrams where they would. There would be boxes and lines, and then they would say, my boxes and lines are a better way of thinking about robotics than your boxes and lines. And then there'd be sort of like an essay and a demo. Right. And then there'd be sort of like, my essay is more convincing than your essay, and my demo is cooler than your demo. But they're incompatible. Always the demos happen to be perfectly compatible with the boxes and the lines. Like these boxes and lines were very good for that demo. But they were thinking about the right sorts of things, and I learned a lot there, and I loved my time. And Gillian Hayes was my master supervisor, and she was amazing. And I got to write a master's thesis on reinforcement learning because at the time I was thinking about, like, I'd read Russell and Norvig, I'd read Sutton and Bartow, and I was like, okay, reinforcement learning is the one true paradigm that captures all this stuff. And I was, as an undergrad, very into behavior-based architectures, and then I realized that they didn't have the math that allowed you to make concrete statements about them, but reinforcement learning did. And so I sort of picked that up. And then when I got to go to the States, I applied fairly widely, and some universities were willing to take a South African and some were not at the time. But I got into UMass, and I got the opportunity to work with Andy Bartow, and he was, that was an amazing experience. Michael knows that I did not enjoy living in the forest, but I did really enjoy that lab, and working with Andy was amazing because he had this sort of big strategic view about how to think of AI and intelligence and the big questions, and he has this anecdote which I like to retell, which is he says that, he would say that you can always take someone else's paper and write a specialization of that paper. And so what that means is that the research space is sort of fractal. You could just continue writing papers that are extensions of other papers. And so it's like very dense, the space that you could write papers in. But Andy thought that the path from sort of here to true AI was like quite short, actually. It was only about 200 papers long, maybe. And so there was a path, and the path was not long, and your job was to be on the path. Your job was to not, in this, but the path was measure zero, right, in this big space. It was this tiny, right, impossibly hard to hit thing, and so your job was not to write a large number of papers. In fact, writing any more than 200 of your career would have been a waste, definitionally, in this circumstance, right? It was really about trying to figure out, what's on the path between here to there. And I really loved that perspective. That was really cool, and my colleagues were amazing. I learned so much from them. A large fraction of them are now on our faculty at really good schools doing really nice work. And
right, and by colleagues you mean your like the other PhD students in the lab.
Yep.
Yeah, they've done remarkably well. It's a great cohort.
Yes, it was quite scary at the time because I'm sure Mark remembers, but reinforcement learning was very uncool. So one of the other
that's what attracted me to it. I'm very uncool.
Well, I like to think that we decided that this was the important question, and so we chased it even though it was uncool, which makes us like some sort of reinforcement learning AI hipsters. Before everyone else realized.
You just got to stay alive long enough for the world to catch up with you.
Yes.
Right, or try not to have ideas that are that far ahead of the curve,
or not give a crap.
Well, I think we should probably land this plane if you guys don't mind.
Well, I don't know. I mean, I agree. We probably should, but there's a ton more to talk about, and all you have is boxes and arrows, and then a demo, and that's bad. I feel seen by that because that's all I have. So I always want to push back against the people who claim math is something other than that. But we can save it. We can save it for another time.
But we can send him that episode of the show. It's devastating to math.
Well, it's how much can you get out of math versus how much does it cost you, like that, and it's certainly possible for everybody to have their own completely unique math, which isn't really that comparable. So how better off are you than boxes and lines and a demo? Well, you don't have a demo anymore. That's what the math gets you.
It's a strict step backwards.
So now what Dave is saying is that math is just a model, and it's not true, but it is useful in some circumstances. Right. I guess that's my counterpoint. Is that at least for me, it just made thinking about things clearer. At least I used to have assumptions when I drew boxes and arrows, and now I know what those assumptions are.
Right.
They're not any better necessarily, but they're written down.
But they're more explicit.
As long as there's still the demo.
Yes.
Fine.
Totally.
George is all about the demo. He's not going to disagree with you there.
Yeah.
He makes things actually move in the real world. It's very cool.
And demo means, whatever it is, it's completely embodied. It's doing whatever it does by itself.
Yep.
Make what judgment of it you wish.
Yep.
Like that. Well, hey, George, this was a whole lot of fun. I sort of feel like we might have met when I was in Providence. I'm not sure, maybe not, but this was a lot of fun.
We met very briefly, and when next
I
in
thought
Providence,
so.
I would like to hash over some of these topics over a gin and tonic that we're down for you.
We got to figure out how to make it happen, assuming that the world if we do ever leave our bubble here in the Southwest, we will make it happen.
Wonderful, and thank you both again for the opportunity. It was great to get to talk to you both.
This was Computing Up. Thanks for listening.